Okay, so welcome to Joerg's third and last lecture. And before he has written all blackboards, let's give him the floor.
Okay, thank you very much for the introduction. Yeah, I just started drawing something that I did on the way, but okay, I didn't quite finish, but I'll do it on the way. Anyway, part 3. That's this lecture. To give it a title, you could call it modular bootstrap. So what we discussed so far was how to use representation theory of Virasoro algebra combined with some relatively standard constructions in the theory of Riemann surfaces in order to define guys called conformal blocks. That is, it was a concrete constructive approach to building families of conformal blocks. I stated the crucial properties which characterize them as a sort of generalized invariance with respect to the Virasoro algebra. Concerning this, here on that board, there's a small correction. I mean, this is not absolutely central for my lectures, but as I don't want to say something wrong, here's a correction. So in this theorem characterizing conformal blocks through analytic continuation of this guy, which we call expectation value of energy momentum tensor, I should have stressed that here we need to consider generic vectors in the representation. So if here was just highest weight vector, this equivalence wouldn't quite work. I don't want to go too much into this. Just let me mention in passing that, you know, we had here, in terms of these conformal Watt identities, a set of invariance condition with respect to the natural action of Virasoro algebra defined by a Riemann surface. This was one way of defining somehow the well, the conformal blocks as a certain type of generalized invariance. And this here is equivalent, it turns out, so which basically characterizes it in terms of, say, analytic function theory in a rather neat way. So this can be useful to keep in mind for having useful alternative definitions of conformal blocks or spaces of conformal blocks. Anyway, forget about this if you like to. This is what I want to continue with. And so the recap, what we shall mainly need in a very schematic form from the last lectures is that the gluing construction lifted to the level of conformal blocks. What it produces is an assignment where I introduced some data, which is on the one hand the decomposition of a Riemann surface into pairs of pans, as can be defined by a collection of simple closed curves on that Riemann surface. So here, let's redraw the picture that goes with it. Here, in that case, we would need 3 such curves. The little gamma is nothing but shorthand for the collection of those. And then I emphasized that on top of that, we need an additional piece of data, which is a tree-balance graph that we can draw on the surface like so. So this would be an example for what can be this so-called pans graph. Okay, so that's the data. And to this, we can assign a family of conformal blocks. And I stressed, okay, rather than considering these invariant functionals, it turns out that basically for all practical purposes, they are characterized by certain functions that the physicists call conformal blocks, namely functions of some gluing parameters Q. And let me anticipate that will become important later. This can be identified with certain coordinates on open sets U sigma inside of the moduli space, let's say MGN of Riemann surfaces. Now, side remark, I will return to it and say a few more words about what's behind later. But that is a useful perspective already to have, that we're locally, that is in some neighborhood of boundary functions on the moduli space of Riemann surfaces. Locally defined, very important point to emphasize here. Good, what is this beta? What is this labeling? So, okay, we're having here a family, if you wish, with beta being, beta being all possible maps from this, from the collection of cutting curves to the Liouville spectrum. That is the set of labels which corresponds to unitary principal series representations of the Virasoro algebra. Okay, so this was basically the output of the last two lectures, the construction, I mean, the sketch of the construction, of course, so I didn't have the time to really present it in full glory of this assignment. And this is what we now want to work with. And what is the main question that this raises? Clearly is, we have chosen lots of auxiliary data in order to get this construction. The question is, how essential is this dependence? So main question is in particular, well, I emphasized, okay, so what are the data which are now so, which we're interested in? Okay, I emphasized last time the dependence on choices of local coordinates around punctures. Let's keep that in mind. It will return a little later in some important way. For now, it's another piece of data that we're interested in, which is the choice of sigma. So that's what we want to study. And well, maybe I can add it here in order to make a smooth transition to the next board where I need to draw pictures. In order to understand it, I want to use a theorem which goes back in slightly or somewhat non-rigorous form to Moore and Seiberg, and one version which I think is mostly accepted to be a rigorous mathematical version thereof is due to Bakalov and Kirillov. And in brief, it says any pair of these objects, sigma 2, sigma 1, can be connected by sequence of what is often called elementary moves. Which will be referred to with the labels B for braiding, F for fusion, and S for modular transformation. And here I started drawing how they look like. You know, this is a pure, if you wish, geometry or even topology statement. I need to define you what these elementary moves relating these decorated Pan's decompositions actually are. Here's the first. It's braiding. It takes place in the three-hole sphere, which we found convenient to redraw by being slightly indecent and look into the pair of Pans from above. Okay, this gives this picture. And then you see here the boundary components, say 1 and 2. And we have here the simple version of the trivalent graph that we have. And what the braiding is supposed to represent is some analytic continuation, where you take here the position of this puncture 1 and the position of puncture 2 and perform the analytic continuation along a path that exchanges the two. The result will produce something where two things have happened, namely the punctures or holes 1 and 2 have exchanged their places. But on the other hand, and for sort of details importantly, you also see that this Pan's graph was somewhat twisted on the way. This is part of the reason why it's useful to have this. With this, you can keep track of braiding. So if you would repeat it, you get 1 and 2 back to their original positions. And it would look like nothing has happened. But, well, you see the Pan's graph has changed. And this is how you see that in terms of these decorated Pan's decompositions, the braiding is a non-trivial operation. Well, the double braiding, which is also called monodromy, is going to be a non-trivial operation, clearly represented by this here twisted one more time. So that's braiding. That is fusion. We've seen fusion already, so maybe I don't need to say so much about it. That is the change of the elementary Pan's decomposition. So here we would have one curve gamma, and here maybe another curve. Well, here I should maybe call it gamma 1, 2. And I should label everybody in the same way as in the first lecture, where we have seen this diagrammatic thing already. And in the second, we have sort of thickened it to a Riemann surface. So I'm just repeating the diagrams that we have seen before here. And yeah, you know, you see here with a naked eye, let me just complete the picture to introducing this Pan's graph like so. There is such an operation that you can simply define by these pictures. But importantly, that's not enough to connect any two pair of such decorated Pan's decompositions on generic Riemann surfaces of arbitrary topology. We need one more crucial thing, which is of course familiar and important for CFT in many ways. You start here with C in C11, and here you start with one standard way of cutting from a curve gamma, and you can change it into another one with the operation called little s. While this operation, which has two effects, on the one hand, we want to change the cutting curve from, we call this here the A cycle, in some terminology that many people will be using. And then here, this will be a D cycle. So you're exchanging the two cycles on the torus. And I also have to tell you what happens to this so-called Pan's graph, or this will look something like, okay, back turns to the vertex. So this would be gamma, and this would be the corresponding gamma prime. So okay, so yes, claim is these three operations. I'm skipping one tiny little detail. Sometimes you should also include the relabeling in the three punctured sphere of the punctures. That's not, I mean, there is one more that you may want to call Z, which is just a relabeling. It doesn't play an important role for us, but it is there if you really want to be accurate in the statement of such a theory. Good. Okay, maybe this is, so this is a topological statement about topology of Riemann surfaces, and that's now what we're going to use. In order to understand how these constructions depend on the choice of sigma, namely it tells us that if we can assign to each of these topological operations linear maps between the spaces of conformal blocks that we construct, that we associate to these data on the left and on the right, then we can relate the spaces of conformal blocks for any pairs sigma 2, sigma 1. Okay. That's the program. Okay. So that's that. Good time. Yeah, that's now the statement I want to make. So it then follows there exist linear relations between f beta 2 sigma 2 of Q and beta 1, sigma 1 of Q for all here sigma 2, sigma 1, if and only if there exist the corresponding relations for the three types of examples that we have drawn there. So if this is true for sigma 2, sigma 1 being one of B, F, or S. That's basically the consequence of Moore-Seiberg-Bacaloff-Kirillov theorem immediately. Good, so B is, I hope here basically everybody knows, we are then thinking about sigma 0, 3. The picture is up there. And the linear relation associated to it takes the form, and really here, if necessary, I'm referring to some introductory lectures to CFT of any kind, basically. We're getting these braiding phases as just a overall factor appearing in this relation. So that would be the form of the relation. That could be slightly more accurate by simply calling this here sigma 0, 3, this well, Hans graph, and this here B dot acting on sigma 0, 3. Just if you want some notations that are useful for stating such a relation here. For F, well, we've seen it, right? Let me nevertheless quickly recall the form. 0, 4 is, and now I'm omitting the arguments because we've seen this relation many times already. Oh, no. That is this integral relation, this all-important integral relation that ultimately was proven by, well, Blanc, Chin, and collaborators. So this, you know, this was basically the missing link between several stories for a long time, and it is therefore great news that now it is there. I'm omitting this. So this relation that we have discussed in somewhat more detail in the first lecture, and we have seen the explicit formula for this here in Chin's talk. So this, I assume, is known for now. This is what represents the fusion move. But yeah, of course, non-trivial, very non-trivial thing remains about S, modular transformation. And yes, here, I think in view of time, I shall maybe just flash the result, make some comments, and then go on. I meant in some first version to tell you a few details which are becoming important now in addition, but I may simply not have the time to do that. So I'm writing down the form, and maybe before I do that, I should point out that this was basically first found by Hadash, Jaskolski, and namely what they observed is that there is a very nice way to relate one punctured torus to the four punctured sphere. Well, it's a kind of classical observation. There's a double covering structure relating these two Riemann surfaces, which implies that we can get S from F. Okay, so it may, of course, maybe somebody can tell me the state of the art. I was trying to look if this is already a theorem in the literature. I think it is not on the archive as far as I could see, but good. On the other hand, we have F now, which was the main great ingredient here. And these people told us how to get S from F. So here comes the form of the relation. And it has a new ingredient, which will be extremely important, although it looks like innocent and is perhaps by practitioners often overlooked. Maybe that is this prefactor. So we're assuming the standard notation Q is e to the q for the modular parameters. And this factor here, which appears, right, which has dependence on the complex structure of the Riemann surface, that's a very important one. Just say it like this. Then there's a kernel S alpha of beta prime. Then we have here the conformal of F beta, say S dot sigma 1,1. Q, well, I'm using here the interpretation of Q's as coordinates on the moduli of Riemann surfaces in order to, often you would like here a Q tilde, which is related by the modular transformation. I just want to stress, we want to emphasize these guys on the same point of the moduli space. So I'm suppressing some pullback in the notations. Good, that's the relation. And that is very important. That completes the list of objects that we need in order to relate any two pairs of Pan's decompositions. So knowing this, we're in business. Yeah, let us maybe say one or two words about this factor. What this is related to, in a way I shall mostly skip, but I want to indicate where it's coming from. We stressed somewhat in the last lecture that there's these dependencies on changes of local coordinates around functors. In the gluing, especially in the gluing, right, you have to say which coordinate neighborhoods with which coordinates you glue. If you change these local coordinates, what you have to use is the transformation of the energy momentum tensor. And recall this had this extra bit. So we had here say squared t of minus c over 12 Schwarzschild w y. From this guy, it follows that if you change the coordinates that you're using in the gluing, the corresponding f function will be multiplied by a factor that only depends, well, that is coming from the Schwarzschild, so it only depends on the change of coordinates that you do, right? So if you change the choices of coordinates, it amounts to multiplying the f's by some factors depending on, well, the coordinates, but of course also on, then thereby on the complex structures that you're considering. And what I am trying to argue or trying to tell you here is this is where this factor is coming from. If you take into account that you have two ways of getting a one-hole torus from the three-punctured sphere. You can use either the coordinates, say where, so you can either think of this as being a, say, cylinder with a puncture, and on the cylinder you have the coordinate w, such that yeah, you have a coordinate w, or you relate this here to the standard picture of the three-punctured sphere, where we have some standard coordinate, I think I call it y, and so the relation then is y is e to the w. It's a relatively standard change of coordinates that is used, so to go from a representation of three-holed or punctured sphere as punctured cylinder to the one on the punctured sphere. And here is a change of coordinates that has a non-trivial Schwarzschild. And what I'm trying to tell is that from the Schwarzschild associated to this change of coordinates, you're getting this factor. If you're thinking carefully about how to glue the one punctured torus, namely here, you can do it by gluing, say, these two guys, something like this, right? You see the torus emerging, well, or doing the same here in the cylinder picture. Okay, so if you do it carefully, and take into account this change of local coordinates business, you will discover that if you write here the conformal blocks, which are coming from this type of gluing, so using the y coordinates, the standard y coordinates on the three punctured sphere, that you will need this additional factor in the modular transformation. It's probably a mostly familiar fact, just maybe it's not always emphasized enough. So anyway, there's this factor and it is coming from this change of local coordinates business. That's maybe the main message I want to tell you here.
Sorry, question.
Yes.
So should the f's under the integrals have the subscript B prime both?
If the f's under the integral should have a subscript beta prime, you're absolutely right. This must be beta prime. That is
And what is the S matrix? Is there an answer for the S matrix coefficients?
Yes, is explicitly known. Was computed from the F by these three colleagues. The type of the answer is going to be S beta prime. So it's similar to the integrals we've seen in Chin's talks or something D or whatever delta. And then there's a quantum dialog, something like this with some exponential functions. That's how it looks. And yeah, so it's explicitly known object. Other questions? Well, okay, so now that we have B, F, and S, we can deduce, thanks to Murseiburg-Bakaylov-Kirillov theorem, the following general form for sigma 2, sigma 1 moves, so the changes of Planck's decomposition. Namely, the general form must be basically as we have seen in the examples already, but now we have here more general notations where Q's are tuples of coordinates, betas are tuples of coordinates, etc. There's some integral kernel here, beta 1, beta 2, and this guy can depend on Q, because there can be Q dependence in these relations, like emphasized here. And then beta 2, sigma 2. Okay, that's the general form. Where, okay, I can observe, you know, just from, I mean, this here is just built by composing these elementary moves, F, B, and S. And from that it follows, well, a simple but important observation on the structure of this. Namely, you can factor out these Q-dependent bits, which are basically just coming from this guy here as an overall factor. And this is, well, simple but important guy. And then there's something here where which really are sort of the most non-trivial part of these integral kernels. But you know, what factors here are the two types of dependencies that matter. This is beta independent, and this is Q independent. And that is a very important fact that this factorization holds. Basically, in CFT literature, first stressed very much by Friedan and Schenker. You know, well, Christoph was asking last time. This is something from which we can hope to get something TQ of T-ish. it's not going to be some TQFT that falls into the axiomatics of Lurie and company, but is something that, for example, Eberhard and company nowadays like to call the Virasoro TQFT. So something that will satisfy a weakened set of axioms that one may still need to formulate.
Sorry, is the claim that V equals E times omega?
Ah, yeah. Thank you. I didn't finish because I was, so V is this. Yes, I didn't finish the formula. That was what I meant to write. Okay. Now, I want to elaborate a little bit on what kind of structure we're seeing here, because we're basically seeing it now in a hands-on generators relations fashion. So what's the kind of global objects that this defines? Global meaning global on the moduli of driven surfaces. In order to do this, and in order to also clarify the mathematical nature of these relations in a different way, let me introduce some notation. And the family of Hilbert spaces, recall we had an interpretation of these fusion relations as a unitary operator in the first lecture. We're now sort of lifting this to arbitrary genus using our combinatorial framework. So what we're doing here is simply to take the spectrum, the set of representation labels that label the principal series representation of Virasoro, and equip it with a scalar product with respect to some measure. We know d mu of sigma with completely analogous definitions in the first lecture, and schematically, I have to be slightly schematic here. This measure is defined by taking the product over the vertices in the Pan's graph of some vertex factors, depending on betas, times the back measure, with, say, a picture defining the notation in one typical example being like this. You have here maybe some beta emerging, maybe here some alpha 1, alpha 2. And what we associated here is CV of beta being the DOZZ formula, being given by the DOZZ formula. So it would be C of alpha 1, alpha 2, and beta V, maybe. Here, introduce labeling for the vertex. Okay, so we're taking here for each pair of Pans a DOZZ factor in order to define our measure. And we want to claim that with respect to this measure, these moves define unitary operators. That's sort of the point. Okay, so that is our space. So here is a theorem I want to note, which basically is a, okay, let me note and then comment on sort of what is going on into it. We define a family of maps that will be recognized as unitary operators relating pairs of Pan's decomposition. By basically taking the kernels that relate conformal blocks and now letting them act on generic elements of this L2 space. So with the notations all in place, it will look like so. Sigma 2. I got the brackets. I need brackets here. Okay, so this is condition, and plain find unitary operators denoted W. Here I should introduce the notation. They go from sigma 2 to sigma 1, sigma 1, sigma 2, and relate the Hilbert spaces to each other. Of course, shouldn't be isomorphic as Hilbert spaces, but it's more structure, making this non-trivial. Okay, emphasis here is on unitarity. What do we need to use to check it? Well, I told you the same statement in the case of the F move. We've seen the B move is represented by a pure face. So the main non-trivial thing to be checked here is that the S is unitary as well. What's it? W is the kernel there, which was the kernel appearing in the relation between for S. The W is the kernel appearing in the relation between the basis of the conformal blocks as introduced there, and the S kernel. Well, okay, I gave a sketch of a few minutes ago.
The unitarity is just follow from the bootstrap formula. Actually, it's a straightforward.
Well, okay, from the bootstrap. I'm not so sure.
I'm sure.
Well, okay. There is probably in your way of looking at it an equivalent way of getting it. Sure, there must be. No, there must be. I fully agree. The original way how it was found was using the relation to quantum Teichmüller, where okay, this admittedly is a somewhat, if not much more roundabout way of proving it, but you can construct these objects in the quantum Teichmüller theory in a completely independent way, which has nothing to do with CFT a priori. And then at some point you're comparing the ingredients FBS, and you see the two things define the same structure of this type, and therefore they're isomorphic. That is sort of the way it was done, but there should definitely be better ways than it was done. Okay, that's the first statement, which I want to stress also to indicate that we're in good shape if we now start interpreting this here as defining vector bundles over moduli of curves, because the vector bundles necessarily have infinite dimensional fibers. The space of conformal blocks is infinite dimensional. And you may wonder sort of what kind of topology gives you control over convergence issues, etc. Here, the Hilbert space structure does the job for you, and therefore one is in good shape. We can speak about bundles of Hilbert spaces. That's why this is important, sort of for having some decent mathematical ground under the feet. Good. Yeah. No, the main point, however, I want to discuss in the rest of this lecture is the global structure that is defined in this way. Let me now just write down here something that I mentioned already in some remarks. We can, well, global structure, global with respect to what? Global in terms of the moduli space of complex structures. Okay, please forgive me abuse of notation. I could probably say something like we fix a topological structure and then we consider the moduli space of all the possible choices of complex structure on the surface of this topological structure. Okay, and what the gluing construction gives us is in fact an assignment. Say now we're talking about just geometry of Riemann surfaces of this data sigma. Recall this was a Pan's decomposition collection of curves and this extra graph. to open charts U sigma in MGN. These are in fact charts which sort of surround boundary components of MGN, where boundary is defined with respect to the Mumford compactification. So from this point of view, we can take the existence of this FE moves. Well, as allowing us to define infinite dimensional vector bundle, or say Hilbert bundle, over the basic idea is extremely simple. You want to read, you know, a vector bundle has transition functions given by linear maps in GL n, c, a complex vector bundle. Now, in the infinite dimensional representation, these matrices representing elements in GL n, c, they can be replaced by integral transformation of the type that we have there. So we just want to read these formulae here. Well, to be more precise, we're talking about the V now. We want to read them as basically defining transition functions for this infinite dimensional Hilbert bundle over MGN.
Yeah, do you expect a vector bundle or a vector bundle with some projective flat?
That's the main point I'm trying to get to. For now, okay, the statement here is the following. We do have sections. Therefore, the thing that is defined from the gluing, the sections being given by the F beta sigma of Q's, the conformal block functions themselves. That is the thing that is defined here that includes, so that we call V, that factorizes into the two parts, is an honest vector bundle. Nothing projective about that. And now we want to take this into the two pieces. We need to extract the topological piece, the W, from the other piece which displays these Q dependence, and see that each factor is really projective only, or projectively flat. But that is sort of jumping ahead of myself, because this is exactly sort of one of the main points I wanted to get to. Okay. So I had a certain build-up. Let me see what I said and what I need to say. Just complete this to begin with for having proper notes here on the board. The fibers are our H sigmas, transition functions. Here are the V sigma 1, sigma 2 kernels or integral operators. That's what I'm talking about with the vector when I speak about the vector bundle. But yeah, let's stress, however, complex structure dependence is only in E sigma 1, sigma 2 of Q. So the question, can we define something like vector bundle double? And yes, okay, I mean, experts will immediately see, well, what's going on, I suppose, from WC. That's the question I want to now discuss. Why would this be a particularly interesting object? W, after all, it was Q independent, was sort of the main feature. And you could hope to make from it a vector bundle, which is not only polymorphic vector bundle, but is much more like a rigid object, vector bundle with a flat connection. A flat vector bundle, another target. Just, I don't know if you're maybe not so familiar, if you have a vector bundle with a flat connection, flatness always allows you to sort of locally in simply connected neighborhoods define to trivialize the connection. That is, a vector bundle with a flat connection is one where you can make the transition functions actually constant in the overlaps, which is of course a much stronger property than being able to make the transition functions holomorphic. So yeah, if you make transition functions constant, you have a vector bundle with a flat connection. Well, answer is almost. Namely, we could write now just by sort of solving for W, bundle-like object that is defined from the conformal blocks in this form. And now we have to talk, and I have to tell you something about this guy, for which, after all, we have a pretty explicit description. We know its transition functions explicitly. That is this funny little prefactor that appeared in the S transformation. What I can tell you is that this defines what is called a projective line bundle. I will say what that is in a moment, because that may be a slightly unfamiliar notion. So let's for now just say it. And here we had noted as the conformal blocks provide sections of that. It is something that has sections, so therefore it must be an honest holomorphic vector bundle. That is what this V object was. And good, the comment on what means projective vector bundle is the following. I had introduced the notation here for the transition functions that define this vector bundle like so. And if I look now on triple overlaps here, so if this here is an overlap, well, it's a triple intersection of open sets, I want to say. And on this triple intersection, sigma 1, sigma 2, sigma 3, and we'll have relations of the following form. There is a violation of the usual cocycle condition that appears in the definition of the usual line bundle, which looks as follows. Where this here importantly is Q independent, and in our case, in U of 1, it's a pure phase. Just a phase that can appear. I will tell you the precise form in a moment, but for now, let us just note, you can, in the spirit of, say, Czech homology, etc., define line bundles in terms of transition functions, which would satisfy a relation like so, without here a factor. And if you allow here some factors, which, well, okay, you have to say in which sort of sheaf they take sections, but if you allow here a violation of this cocycle condition, then you call it a projective line bundle, terminology that I think also was first proposed by Fiedler and Schenker. Okay, so that's yeah.
Does it mean that there's a germ in the background?
I think so, yeah. It's just what you, I mean, if you simply adopt the check approach to gerbs, you can make a gerb from the state. Last comments are already approaching the end. It's good time. Yeah, so we have here something that is on a vector bundle. We have here something that has this violation of the co-cycle conditions characterizing a vector bundle. So this here must also have a violation of being an honest vector bundle. And it is, yeah, it is this. What is it? It's a projectively flat. Pillar. In other words, if I look at the transition functions, which are now these unitary operators, right? So here now we're thinking about unitary operators. And also there, I will find a violation of the co-cycle condition, and it has to be just the inverse of the one which appears in the definition of this line bundle EC. Hybrid mark. Yeah, this is an important piece of structure that comes with any CFT. And the mathematical way somehow to formulate it or to describe it is to say, if we're thinking in terms of check homology, then this defines a class in the second check homology of n bar Gn. You have to compactify it U-Mumford and U1. And I want to describe here why U1 and how it looks a little more explicitly in the remaining few minutes. So for now, so a comment. Stress that using our hands-on generators and relations type description, we can compute it fully explicitly. And I'll tell you roughly how that works, and then we'll conclude. Maybe one or two comments. Using this couple of relations, which are the relations. So what these people have found is a kind of minimal set of relations among the B, F, and S moves that imply all others. Of course, now I can speak of the topological relations. This is really what sort of this theorem is about, but now it's lifted. We know the same relations must be satisfied by the integral transformations that we associate with relating conformal blocks. I don't want to write down the full list. This would take me another half an hour to write out with all the indices and arguments and so on. But the form is easy. It's kind of, or some formal schematic features are perhaps easy and useful to appreciate. So what relations do we have? What's the type of relations? The relations, for example, of the type B, F, B, and this is often called hexagon, because you simply associate each of the things here to a corner of a hexagon, and then going round and closing the hexagon is what this expresses, that you can close the hexagon. Or there's F, F, F. Right, so here you should see there's some integral in beta, and then the arguments you have the beta somewhere, and this is then the product of two F's. Well, we've seen it in Finn's talk. So these are the relations for g equals to 0. And what is of most interest for us now is for g equals to 1, we have 3 additional relations, which roughly speaking look as follows. S squared is the inverse. Then ST S is t to the minus 1 S t to the minus 1, where we're introducing here some notation T for what's called beam twist, and it can be represented as the product of 2 braidings with some, and it will be represented by, again, a pure phase, e to the minus 2 pi I delta beta. So it describes something that most of you will have seen. So if here is an edge of this graph gamma running through, which is, and we're having here some cutting curve like gamma labeled by representation labeled beta, this will correspond to twisting this around and otherwise keeping the setup. And it gives a multiplication by such a phase. It's well known that mapping class group is generated from these operations. Good. And last but not least, well, here, okay, something is to be put here. And then there is a complicated relation, which, however, does something simple in the end. It looks like S, F, T, T inverse F. This here representing a monodromy along a cycle of 1 punctured torus, twice punctured torus, sorry. And here we have F, D, F, this little a and this little b. So this really just says that modular transformation S exchanges monodromies along A and B cycle. That's the full list of relations. And now you can even, you can use this description of this pan-screwpoid, that's how this object is called, in order to quite easily classify central extensions, right? Because you can see that, good, there is a distinguished normalization for B, allowing you to remove here a possible phase from this relation. Having done so, well, you need to check that, well, then you can fix the normalization for F, removing a phase from this relation. To go on in this way, well, this doesn't help you much. B now was fixed. So if you want no phase here, it fixes the normalization of operator S. But then we're done. Then we have no longer any freedom in the redefinition of basic generators to remove possible phases here. The statement is, there is a phase generically here. And this is the only non-trivial case where this co-cycle chi here can be non-trivial in this particular representation. So here, this is what now plays the role of sigma 1, sigma 2, sigma 3. If you take the appropriate values here of the sigmas. And now I'm telling you what the computation gives, which you can simply do with the help of the explicit formulae that I've written. Again, I guess experts will hardly be surprised. So there's a 6 pi I, and then there's this famous C over 24 that kind of appears all over the place. That is what gives this phase. And we see now with the naked eye, it's a universal object. that appears here representing the central extension. So this was basically the point that Friedan and Schenker had first emphasized, that there is in the description of conformal field theories on Riemann surfaces, there's a nice interplay or working together between two aspects. There's some universal aspect which just has to do with this distinguished class in H2 associated to the moduli spaces of Riemann surfaces. This takes care of central charge. It's universal, just knows what central charge. And then there are these other objects which define a projectively flat line bundle. But this projectiveness, again, must be necessarily controlled by this. And apart from this projectiveness, yeah, it's just a good ordinary vector bundle. Or here bundle, I mean Hilbert bundle. Okay, I think I'm at the end. I'm also running out of time. So as a summary, let me just note basically the upshot lectures. To sum up all what I tried to say here is that the Liouville conformal blocks, they define some gadget that is under the name of a modular functor. I have introduced the definition here, but basically it is the structure that is having these gluing relations and then consequently the linear relations between the bases that are associated to different gluing patterns. So roughly speaking, you can define this structure if you want generators in relations fashion in terms of F and S. And in the relations, I want to stress, there's one piece of data that is non-trivial, that is not completely universal, namely the chi, but it is fixed once we have fixed the central charge. And the very last word for Christoph and others, I hope. What this is the basis for is what is nowadays by some people called Virasoro TQFT. And as I said on the way, I think to understand more precisely how much, to what extent it really is TQFT and what extent it is not, still seems interesting question to me. Thank you.
Thank you very much for this nice set of lectures. We have time for questions.
This construction has been generalized for like conformal block of extended algebras. Like
yes and no, right? So, okay, you can go on to say Toda W as next step, right? So, and there I would have high hopes that this is sort of around the corner, where we have to be precise in what we mean by saying has been generalized. The key ingredient here, the main non-trivial technicality, was the existence of these F, B, and S moves, which basically boils down to the F as the main non-trivial one. This is sort of the key like technicality that you need to solve. And this, for example, has not, I mean, it is known for like minimal models or say compact Westermino-Witten and so on. For this, you can use all this formalism as is, right? Just then you replace the Hilbert spaces by finite dimensional vector spaces and so on. That is all well known and not any problem. For W, where you expect again infinite dimensional Hilbert spaces, yeah, problem is with the F. Right? Nobody has constructed the F for, say, even SL3 Toda W conformal blocks. And the extra issue is very simple to see, but very hard to solve, which is that you're going to have infinite dimensional spaces of vertex operators or intertwiners for the three punctured sphere already. Mm-hmm. You have to label those. You have to equip them with a Hilbert structure. You have to maybe then understand non-trivial moves, which have to do with the rotation of boundary components. This is an extremely fascinating project for the future, I would say, because that's hard.
Is there a nice way to control the behavior of the conformal block when you shrink one of the curve gamma?
Well, in the way I described it, it is basically controlled by the fact that we are actually constructing, at least in one suitable basis, things that just are power series in the gluing parameters. And therefore, I read from the form of this power series, it is something like q to the external dimensions times sums in powers of gluing parameters. So from this type of gluing construction, it is relatively easy to control.
When you shrink one of the gammas, this will, the leading term will correspond to insert a vertex operator there, and then there is descendant, and can you control
well, okay. It depends a little bit on how ambitious your question ultimately really is. So you can, I'm certainly unable to compute higher orders in this series explicitly. In very few cases.
Virasoro should act because it's
the leading order. The leading order follows basically immediately from this construction. The higher orders are hard, and sort of it was. In some sense, this was what was great about AGT, that for a four-punctured sphere, for example, gave explicit formulae for these higher orders.
Make your question more ambitious. If you look at this factorization, you can hope to learn something about duality, in which way representations are dual. This shouldn't be rigid duality anymore because your system is intrinsically infinite dimensional. Is there a chance to learn something?
Okay, can you?
Well, if you're
might be stuck at the word duality.
Well, if you're
which of the dualities are you referring to?
If you're factorizing if a representation and a contract-mediate representation.
Yeah. Okay. So here it's very simple because we have this isomorphism between representation and contract gradient representation.